Why is this showing? Alright. So okay. So for hmm? Yeah. For your product poly and your sum poly, you implemented a couple methods, right? You implemented evaluates, partial evaluates, and degree, right? There's one more that I want to talk about, which is reduce. Okay? So the goal of reduce is to give you the evaluations over the Boolean hypercube. That's just the goal of reduce. It gives you the evaluation of that like composed polynomial over the Boolean hypercube. That way you can now like um let's say sum it up or blah blah blah. Does that make sense? So let me give an example. Let's say we had 2ab, right? And we had 3ab. Okay? We can represent this using a product poly, right? Make sense? But in so if we multiply this out properly, that'll be what? 6a square b square. Now the evaluation of this polynomial over the Boolean hypercube is right. Make sense? But then this product poly is going to be, this one is what? And this one is, right? So what reduce does is that it just takes the evaluation forms that it's holding, and then it just does element wise whatever the operation is. Yeah. So for product poly, it's going to do element wise multiplication. So this is going to give us 0, 0, 0, 6. This doesn't mean that this is the representation of 6a square b square, because that's quadratic. But we're saying that this is the evaluation of this over the Boolean hypercube, right? Yeah. Now let's do for sum. So if we had 2ab, 3ab, and it was a sum poly, this would be what? 0, 0, 0, 2, right? Well, me, I'm seeing sum poly as just like taking two things that is summing. Whether it's the two things are like sum polys or not. We'll still do another one now for like sum of product polys. Okay? And this one is what? 0, 0, 0, 3, right? So the reduce is supposed to give us 0, 0, 0, 5. This is what reduce is supposed to give us. So we call this sum poly the reduce. We should get the evaluation of the two polynomials over the Boolean hypercube, assuming you had like summed them up and everything. So if you had actually summed them up, that would be 2ab plus what? 3ab, right? That's 5ab. If you write at 0, 0, that's 0. Write at 0, 1, that's 1. Right? No? 1, 0, 1, 1. Which is exactly the same thing that we got here. Right? Now let's do something more complicated. Let's do a sum poly that is made up of product polys. Okay? So we have a sum poly that is made up of a product poly. So what should we multiply? Then what should we use for the other one? Yeah, it has to be the same. AB plus,
Seven.
no comma,
Yeah, comma seven.
comma 7 AB. Right? Now let's reduce this polynomial to like one polynomial. Okay? So product poly would be 6a squared b squared, right? That's for this one. This other one will be what? 7a squared b squared, right?
Yeah.
And the summation will just be 6a squared b squared plus 7a squared b squared.
That's
Now let's evaluate. Oh, they're the same, yeah. This is not an interesting example because it's just like a squared b squared, but it's fine. So now we evaluate this over the Boolean hypercube, right? That's what 0 0 will give us 0. It's too simple of an example, but 13. So when you have combined everything and you evaluate over the Boolean hypercube, you get this. So now the question is, can you also get this without like combining everything? That's where what we're talking about comes in. So the way you do you call reduce. So how you do that is like you call reduce on the on the situation whereby if you call reduce on this, you will get back. That's the goal, right? So each of them are represented with evaluation form, right? So when you call reduce on some poly will now call reduce on each of its children, right? Then product poly will call reduce on each of its children. But when product poly has gotten it to multiply them together. So we'll call some poly dot reduce. So what it's going to do is going to say like, let's call this one P1 and call this one P2, okay? It's going to say P1 dot reduce plus P2 dot reduce. Right, because it's like sum poly. So it sums the distance. But then this product poly is now going to like, it has 2AB and 3AB, right? 2AB is what? And 3AB is what? So this product poly, to reduce is to multiply all its children, right? So this will give us what? This other one will call on its children, which is what? AB and 7AB. AB is what? And 7AB is products, right? Make sense? Now that's the answer to this and the answer to this. Then this one will now add them together. Do you understand? Which is exactly the same thing that we were expecting. Does this make sense? So basically you can take a polynomial that has not been fully multiplied out, but has been represented in this product poly, sum poly, and then you can get the evaluations of that polynomial over the Boolean hypercube. Does that make sense? No, product multiplication. So that will be the answer to reduce in product poly. But for sum poly, it will call addition. But from the result of like product, the first product poly will reduce, yeah, then reduce, then sum. So you get the evaluation. Exactly. Exactly. Yeah. So, you said? Yeah, so inside the product poly is already in, product poly, multilinear poly. So it's already evaluation form, yeah. But then this, so when you call reduce, it will now do like element-wise multiplication of all the multilinear polynomials to give you just one multilinear polynomial. And how to flatten it. But you don't use this for your round poly. You only use it for your, what am I saying? Hmm? Yeah. So in some check, when you want to get your round poly, you know normally like you sum over a regular sum check where it is not quadratic, where it is linear. To get your round poly, you take your evaluation array, right? And then you split it into two, right? So you take this entire thing and then you sum it up. And then this will be the first element in your round poly. Then you take the remaining and then you sum it up also. And then this will be the second element in your round poly. So this is like your round poly. But then this first one here is, these are all the places where a is equal to 0. Right? So a is 0, a is 0, a is 0, a is 0. The second one is where a is equal to 1. So another way to get this like half is basically just partially evaluating your at where a is equal to 0. So you partially evaluate this at 0, bc to get f of bc, you will get this. Alright? And to get this other one, you do f of what? 1 bc. So that will give you this one where a is 1. It's like you're already fixing a to be 0 here, which fixes, it just picks out those ones. And now when you're fixing a to be 1, so it just picks out those ones. But this was sufficient for previous sum check because of we only need to send evaluation at 0 and evaluation at 1. Now we're going to send in 0, 1, and 2. So there's no such thing as breaking it in half anymore because we only have for 0 and 1. So instead, what we'll do is you can still break in half for like the first two, but then you need to evaluate. But the general idea is that you take this partial evaluation route. Okay? So you partially evaluate a equals 0, you get a polynomial. So if this polynomial is a sum poly or product poly thing, when you partially evaluate at 0, you're still going to get another sum poly with product poly, right? Because partial evaluation is not really changing it, it's just mapping over each one, right? So what happens is that to now get this thing, you now call reduce. Yes. Yeah. So like, let's say this was your FABC, right? And you wanted to send your first f of a polynomial to the prover. But then this FABC is a degree 2, variable degree 2, right? So that means that you cannot just send 0, 1. You have to send 0, 1, 2. So the way to do that is you partially evaluate, which you have already implemented for sum poly and product poly. This will now still be like a sum poly, product poly, right? So what you now do is now call dots, which now give you like a vec of f, which will represent the first half. Then you now do dots. Then that will now be the entry. Yeah, so you do setting for F1. Yeah. So normally, it's like you skip A and you sum the rest of them over the Boolean hypercube. Alright? But another way to do it is that you get the first half, second half. And that's the same thing as partially evaluating the first A at 0 and partially evaluating A at 1. Then summing. So now the same thing here. Rather than skipping A, you partially evaluate A at 0, A at 1, and A at 2. Then you call reduce, which will give you like the first half, the second half, but then there's a third half somewhere. Alright? Basically what we're trying to get is we're trying to get all the places where this one will give us all the places where A starts at 0. Right, so that's 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. This other one will give us where it's 1. Why this one give us where it is 2? The normal way you would do it, right, is you would do f of A, then you sum BC over the Boolean hypercube, right? So that's supposed to give you like A 0 0, A 0 1, A 1 0, A 1 1, right? This is supposed to be your f of A, right? But then this f of A is quadratic, right? So to actually get like the evaluation form representation for this, you need to evaluate at 3 points, right? So you do f of A where A is 0, which will give you, then you do f of A where A is equal to 1, then you do f of A where A is equal to 2. And those will be the 3 points that you will send. But this one is kind of like doing it. Yes. You get it now. So we're still like skipping and summing over the Boolean hypercube, but these are giving us like f of A in like coefficient form, right? Then we cannot evaluate f of A at like 0, 1, 2, so that we can convert it to evaluation form. If I evaluate at 8, 0, then this will change all to all zeros, right? Which is exactly what we did here. If I evaluate at 1, this will change to all 1s, which is exactly what we did here. I evaluate at 2, this will change to all 2s. Then we'll put everything in an array. But that's what the first half sum and second half sum was already doing for you automatically. But now it's like we're now doing for 3. Because we already know beforehand that it's like quadratic.
That means that nothing changes actually. Just like that,
Yeah. Since. Okay. So I'll stop the recording here. Then let me just stop the recording, and I'll